Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Master's Degree Programs. Master of Science, Renewable Energy and Environment, MSCRWEE. SEM MRW 001 Energy Conversion. Block-2 Steam Nozzles and Turbines. Unit 6 Regeneration, Reheat and Intercooling. 6.1 Introduction. The fundamental forms of energy with which thermal power plants are primarily concerned are heat and work. Heat gets converted into work. In a heat cycle, the working medium receives heat at a given temperature from a heat source, converts part of it into work and discards the remainder to the receiver. The next cycle then follows. The study of these cycles belongs to the realm of thermodynamics and is an essential aspect of thermal power stations. A cycle which uses heat in an ideal or reversible manner to produce work from the available energy is called an ideal cycle. In actual practice, however, the imperfection in the processes of working medium cause a reduction in the production of work from the available energy with the result that some of the available energy is also discarded to the receiver. Thus, there is a reduction of the cycle efficiency, since it depends on the output of the work done. To improve the overall performance of the cycle, arrangements like intercooling, reheating and regeneration are provided with the basic power cycle. These additional systems help in improving the overall efficiency of the power plant. Objectives. After studying this unit, you should be able to understand the fundamentals of regeneration, reheat and intercooling processes used in power plants, and their effects on the cycle efficiencies of steam power plant and also the gas power plant. 6.2 Regeneration, reheat and intercooling processes. The processes of regeneration, reheat and intercooling differ from that of the steam power plant to gas turbine plant, since the steam power plant makes use of vapor power cycles whereas the gas turbine power plant makes use of gas power cycles. In the following two sections we shall study these three processes in two different types of power plants. 6th February 2001 Processes of regeneration and reheat in steam power plant. Regeneration process. This process is an attempt to induce reversibility in an ordinary Rankine cycle-based power plant so as to increase its efficiency. The mixing of cold condensate with the saturated steam and water mixture in the boiler constitute the principal irreversible processes of the cycle. And regeneration aims at reducing this irreversibility by heating the feed water near to the saturation temperature through the utilization of heat of steam which has partially expanded in the prime mover. Since the purpose is the thermal regeneration of condensate, the cycle is known regenerative cycle. Reheat process. As the initial pressure of steam is raised beyond 413.7 NSQ cm absolute to attain greater thermal efficiencies, it is found that resulting condition of steam after expansion is increasingly wetter and exceeds the safe limit of 12% condensation. Therefore, becomes necessary to reheat the steam after part of its expansion is over so that the resulting condition after complete expansion falls within the region of permissible wetness. This reheating or recuperating of steam is now universally used when high pressure and high temperature steam conditions such as 965 to 2413 NSQ, SEM and 510 to 620 degrees Celsius are employed for the throttle. For plants of still higher pressures and temperatures, a double reheating may be used. Although reheating was basically introduced as a device to reduce wetness in the final state of steam, it is found that there is an improvement in the cycle efficiency as well. Thus, the benefits of reheat are twofold, viz. It makes high initial pressure and temperature possible, this increasing thermal efficiency, and in itself, it improves the plant efficiency. 6th February 2002 processes turbine power plant of regeneration, reheat and intercooling in gas turbine power plant. Regeneration process. Exhaust gases from the turbine which have a substantial heat content can be utilized to heat the compressed air which is supplied for combustion in the combustor. Such heating of combustion air is known as regeneration, and the heat exchanger transferring heat from gas to air is called regenerator. To obtain maximum gain from regeneration, it is essential to prevent the pressure drop in air since the cycle efficiency depends upon the cycle pressure ratios. With the good working arrangement, it may be possible to obtain 50% to 70% of heat recovery in the regenerator. Regeneration helps in increasing the final temperature of the gas before it enters the turbines, and this temperature rise is an important factor in controlling the plant thermal efficiency. The effect of regeneration in gas cycles is a reduction of the optimum pressure ratio. In an ideal case, the efficiency continually increases as pressure ratios decrease. Intercooling process. Since most of the output of a turbine is consumed by the compressor, the actual efficiency of the gas power cycle greatly depends upon an efficient working of the compressor. The power required for the compressor is affected by the temperature of air under compression. If the air can be cooled after a part of the compression process has completed, the total compressor work could be reduced, and at the same time greater weight of air could be compressed by the same compressor. To attain higher compression ratios, it is necessary to use multistage with intercooling. Since a bulk of the power developed by the turbine is used at 2, driving the compressor, a reduction in compressor work is desirable to increase the power output of the plant. One of the ways to achieve this is to cool the air after it has been partially compressed, and this is accomplished by employing multi-stage compression and intercooling between stages. Intercooling improves the thermal efficiency, air rate, and work ratio. Thus, if the intercooling is used, the size of the turbine and compressor can be reduced for the same output, or alternatively, greater work can be obtained from the plant of the same size by employing multi-stage compression with intercooling between stages. The compression process in the compressor can be made to approach isothermal compression, which requires less power than the adiabatic compression. In an ideal state of intercooling, the fluid should be cooled to its ambient temperature, i.e., the temperature of the fluid before compression in each stage, and there should be no loss of pressure in this system. Also, the maximum advantage of intercooling is when the pressure ratio in each stage is same. Maximum advantage of intercooling occurs when pressure ratio is high. Compression Efficiency is low and regeneration is employed. Reheating process. By using multi-stage turbine, the gas after expanding in the first stage is taken to a reheater, which is an additional combustor, and reheated to the original temperature. This reheated gas is expanded in the following turbine stage. In a three-stage reheating system, the exhaust from the second stage of the turbine is sent through a secondary heat combustor before being expanded through the final stage. There is a limit to pressure ratio for substantial improvement in thermal efficiency, though there is little effect on air rate and work ratio. Also, reheating has little effect in the absence of regeneration. Reheating involves extra equipment of combustor and high temperature resistant material for construction, which adds to cost. Also, the complication of splitting the turbine and providing suitable controls may offset much of the gain by use of reheater in many cases. 6.3 Thermodynamic cycles of regeneration and reheat for steam power plants. A steam power plant based on a simple Rankine cycle has a very low efficiency. By adding regeneration and reheat processes, the overall efficiency of the steam power plant can be considerably improved. In the following two sections, we shall discuss two thermodynamic cycles, namely regeneration cycle and reheat cycle. These are nothing but the modifications of the simple Rankine cycle. 6 March 2001 Regenerative steam cycle. This type of cycle is obtained by inducing reversibility in the ordinary Rankine cycle for increasing its efficiency. In Rankine cycle, the mixing of cold condensate with saturated steam and water mixture of boiler makes the irreversible process of the cycle. Regeneration helps in reducing this irreversibility by heating feed water near the saturation temperature. This is done by utilizing heat of the steam which has partially expanded in the prime mover. This cycle is called regenerative because the purpose is the thermal regeneration of condensate. In regenerative feed water heating, a fraction of the steam flowing through the prime mover is extracted or bled at certain points in the expansion, and its remaining heat is utilized to preheat the feed water. This heating of water approximates to reversible heating and results in improving the cycle efficiency. The heat of the extracted steam, which would have otherwise been lost to the condenser circulating water, is thus transferred to the cycle itself. There is a reduction in actual work output for each unit of steam weight, but due to a much greater reduction in the quantity of heat required to be added to the boiler, the cycle efficiency is greater. The schematic arrangement of the cycle using two heaters and its representation on temperature entropy plane are shown in figure 6.1. The points 5, 6, 7, 8, 9 and 10 are actual state points of the liquid, but the effect of feed water heating can be considered as increasing the enthalpy of the water at every stage in such way that the area 5-6-8-10 SRQP represents the energy that is reduced from the total work area and added to the feed water. The overall effect is that the condensate entry point into the boiler is shifted from the point 6 to the point 10. The net area 1/4 PTRS10 now represents the ideal turbine output. If W1 and W2 are quantities of extraction for unit weight of steam entering at the throttle, then 1 unit of steam flows from 1 to 2. 1. W1 from 2 to 3 and 1 W1 W2 from 3 to 4. Therefore, If the pump work is neglected, the ideal efficiency of the cycle can be expressed as: look at the screen. Figure 6.1, Regenerative Steam Cycle. It would be found that for each additional heater in the cycle, the efficiency increases. However, after the first heater, the increase through each additional heater successively diminishes until the gain reduces to a point where the capital cost of additional heater and pump would not be justified. This gives a practical limit to the number of heaters required. Theoretically, the efficiency of the cycle would approach the Carnot cycle efficiency if an infinite number of heaters are used. In actual practice, not more than 5 bleeds are usually employed. While locating the bleed points, they should be arranged in such a way that the enthalpy rise in each heater equals the enthalpy difference of saturated water in the condenser and in the boiler divided by the number of heaters plus 1. Table 6.1 shows the effect of the addition of feed water heaters on heat gain. Table 6.1 Effect of feed water heaters. Look at the screen. In current practice, economic consideration favors the use of heaters on the pattern shown in Table 6.2. Table 6.2 Number of heaters to be used for a specific capacity of turbine. Economic consideration. In the cascading system, which uses all closed heaters, the bled steam condensate from the high-pressure heater collects in heater hot well and flows to the low-pressure heater. Due to the reduction in pressure, a part of the condensate flashes into the steam and contributes towards enthalpy increase of the main condensate. Since the degree of low pressure attained is reduced with the arrangement, there is a loss in cycle efficiency, but the cost of the pump is saved. In actual practice, however, several factors contribute to reduce the gain in efficiency. These are: drop in the bleeder pipes, heater terminal temperature difference in temperature between the saturated temperature corresponding to the steam pressure within the heater and the temperature of feed water leaving the heater, flashing of heater drains to lower pressure. Unequal feed water temperature rises across successive heaters, evaporation of makeup, subcooling of condensate in condenser hot well and extra pumping power required, etc. 6 March 2002 Reheat steam cycle. It is necessary to reheat the steam after part of its expansion is over so that the resulting conditions after complete expansion falls within the region of permissible wetness. This reheating or recuperating of steam is now universally used when high pressure and high temperature steam conditions, such as 98 to 246 kg Cm2 and 510 to 620 degrees Celsius are employed for the throttle. 4. Plants of still higher pressures and temperatures, a double reheating may be used. In its simplest form, the cycle involves withdrawing the steam from the turbine at some intermediate stage, returning it to the steam generator, where a separate superheater is provided in the gas bath for recuperating the steam, after which it is reintroduced into the turbine at following stage. Reheating process not only helps in reducing the wetness of the steam in final stage, but at the same time improves the cycle efficiency. Thus, the benefits of reheat are: it makes use of high initial pressure and temperature, hence increasing thermal efficiency, and it improves the plant efficiency. The reason for this gain is the increase in the average temperature at which heat is added to the cycle. In modern plants, reheat is always used with regeneration. The schematic arrangement of reheat cycle and its representation on temperature entropy plane are shown in Figure 6.2. Look at the screen. Figure 6.2. Reheat steam cycle. The heating alone, 2 to 3, takes place in the reheater. If H1 is the heat added to the conventional boiler, H2-3 is the heat added during reheat, H4 is the heat content of steam at the final exit to the condenser, and HF is the heat of saturated water supplied to the boiler. Then, reheat cycle efficiency, NRE, may be written as NRE is equal to H1 plus H2-3 minus H4 upon H1 plus H2-3 minus HF.6.2. In actual practice, reheat improves the cycle efficiency by about 5% for a typical 84.414.06 kgcm2 cycle. A secondary heat will give a much less gain, while capital cost involved would be so high as to prohibit the use of two-stage reheat except in case of very high initial throttle conditions. The cost of reheat equipment consisting of boiler, piping and controls may be 5 to 10% more than that of the conventional boilers. This additional expenditure is justified only if gain in thermal efficiency is sufficient to promise a return of this investment. Usually a plant with a base load capacity of 50,000 kilowatts and initial steam pressure of over 42.18 kgcm2 would economically justify the extra cost of reheating. Another disadvantage of reheating is the difficulty in governing the speeds of prime movers, for which special interceptor valves controlled by the main governor have to be used in the reheater circuit. Since some steam is always stored in the reheater and piping system, the high pressure and low pressure stages of the turbine would continue to get power unless separate control is effected simultaneously with the main governor action. The interceptor valves operate when the prime mover speed increases by 3 to 4% above normal. In actual practice, there is a tendency to eliminate some of the safety devices as the actual operation has been found to be somewhat less complicated than expected. The improvement in thermal efficiency of the steam power cycle due to reheat is greatly dependent upon the reheat pressure with respect to original pressure of steam. Broadly, the exhaust pressure for the high-pressure turbine should be approximately 1/6 to 1st April of the initial pressure depending upon the initial temperature. 6.4 Thermodynamic cycles of regeneration. Reheat and intercooling for gas turbine power plants. A simple gas turbine plant consists of the turbine itself, a compressor mounted on the same shaft or coupled to the turbine, the combustor, and auxiliaries, such as starting device, auxiliary lubrication system, fuel system, the duct system, etc. A modified plant may have, in addition to the above, an intercooler, a regenerator and a reheater. By adding the regenerator to the gas turbine cycle, the efficiency of the cycle can be improved. The intercoolers, another heat exchanger which cools the partly compressed air so that its volume is reduced and density increased. There is a considerable saving in compressor power due to intercooling. So, an intercooler improves compressor performance. A reheat improves the output from the turbine due to multiple heating. 6 April 2001 Regenerative gas cycle. Exhaust gases from the turbine which have a substantial heat content can be utilized to heat the compressed air which is supplied for combustion in the combustor. This exchange of heat takes place in a device called the regenerator. It is usually of shell and tube construction. The exhaust gases are made to flow inside the nest of the tubes whereas air flows outside the tubes. In the shell encounter flow and is heated up by the heat given out by the gases. The effectiveness of heat transfer depends upon the area of the heat transfer surface. The use of regenerator to heat combustion air reduces fuel consumption of the plant and this improves the cycle thermal efficiency. Beginning. Efficiency is greater at lower pressure ratios. There is practically no effect on net work produced or on the air rate. There is a drop of about 5% in absolute pressure at compressor outlet due to the passage of air and gas through the regenerator, although theoretically the regeneration process takes place at constant pressure. If the temperature of the air changes from T1 to T2 and the initial temperature of flue gases is Tf1, the effectiveness of the regenerator is given by ERG is equal to actual heat transfer upon limiting heat transfer is equal to Ta2 minus Ta1 upon Tf1 minus Ta1.6.3. The heat transfer through the regenerator can be improved by increasing the area of the surface and also turbulence of flow. However, increasing the area of contact surface involves higher initial cost for the regenerator, while increasing the turbulence causes an increase in the pressure drop. The regenerator has, therefore, to be designed as a compromise between the gain in heat recovery on the one hand and increased cost due to higher capital and operating costs on the other. The schematic arrangement of the regenerative cycle and its representation on the pressure volume plane are shown in Figure 6.3. Figure 6.3, Schematic arrangement of regeneration gas cycle. Look at the screen. 6 April 2002 Reheat gas cycle. The reheating improves the output from the turbine due to multistage heating. Reheater can be treated as an additional combustor. By using a multistage turbine, the gas after expanding in the first stage is taken to a reheater and reheated to the original temperature. This reheated gas is expanded in the following turbine stage. The schematic arrangement of reheat gas turbine cycle and its representation on pressure volume plane are shown in Figure 6.4a and 6.4b, respectively. Figure 6.4, a reheat in gas turbine cycle. Figure 6.4b, pressure volume diagram of reheat gas cycle. 6 April 2003 intercooling gas cycle. Since a bulk of power developed by the turbine is used up in driving the compressor, a reduction in compressor work is desirable to increase the power output of the plant. One of the ways to achieve this is to cool the air after it has been partially compressed. This is accomplished by employing multistage compression and intercooling between the stages. Generally, 2 to 3 stages of compression are used. Intercooling improves the thermal efficiency, air rate and work ratio. Thus, if intercooling is used, the size of the turbine and compressor can be reduced for the same output, or alternatively greater work can be obtained from the plant of the same size by employing multi-stage compressor with intercooling between the stages. The compression process in the compressor can be made to approach isothermal compression, which requires less power than the adiabatic Compression. In the ideal state of intercooling, the fluid should be cooled to its ambient temperature, i.e., the temperature of fluid before compression. In each stage, there should be no loss of pressure in the system. Also, the maximum advantage of intercooling is obtained when the pressure ratio for each stage reaches n-third of the overall pressure ratio. The schematic diagram of gas cycle with intercooling and its representation on PV diagram are shown in figure 6.5, 8, and 6.5b, respectively. Figure 6.5, a multi-stage compression with intercooling. Look at the screen. Figure 6.5, a multi-stage compression with intercooling. 6th April 2004 gas cycle with regeneration, reheat and intercooling. We have already discussed, separately in the previous sections, the effects of regeneration, reheat and intercooling respectively on gas cycle. In actual practice, all these modifications, with regeneration, reheating, and intercooling, are combined in a simple modified cycle, and a substantial gain in the overall plant efficiency is attained. Such an arrangement is shown in figure 6.6a, and its representation on a pressure volume plane is shown in figure 6.6b. There may be one or more stages of reheat and intercooling. The arrangement shown has one stage only of each of modifications. Figure 6.6, a arrangement of regeneration, reheat and intercooling in gas cycle. Look at the screen. Figure 6.6, BPV diagram of the combined gas cycle using 6.5 summary. In steam power plant, the purpose of regenerator is to heat feed water by utilizing the heat of steam partially expanded in the prime mover, this reducing the irreversibility and increasing the plant efficiency. 2. The purpose of reheating is to achieve desired wetness of the steam by heating it after part of its expansion from the turbine, thus increasing the cycle efficiency. In gas turbine power plant, the purpose of regeneration is to preheat the air entering the combustion by using the heat of exhaust gases to increase cycle efficiency. 2. The purpose of reheating is to heat the working gas after its expansion from the first stage of the turbine to regain its original temperatures. 2. Increase thermal efficiency as well as plant efficiency. 3. The purpose of intercooling is to reduce the compressor work, increase the power output of the plant and improve thermal efficiency, air rate, and work ratio. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.